Swayam Prabha. Digital India. Educated India.
Core electrons, valence electrons. I got two new terms, core electrons and valence electrons. Core electrons are the ones who are closely attached to the nucleus. Closely attached. They don't want to leave the nucleus. Right? Like a baby, always want to be around with mom. Okay. Once you grow up, like at this stage, you don't like to listen to Papa and Mama. Whatever they say, you don't like, right? So these are the ones they want to be set free. Right? So these are called valence electrons who are very loosely attached. So, since core electrons are tightly attached to the nucleus, they do not contribute to the property of the system. They stay with the nucleus. Okay? Like here, your 1s orbitals are very close here. Since they do not contribute to the property of the system, we try to treat nucleus plus core electron as a single electron together. Nucleus plus core electron will treat as ion. Correct? Nucleus and core electron ion. Sodium ion, you know, right? What is sodium ion? What is sodium ion? I know, but how many electrons are there in sodium? So it has total how many? One atom, sodium atom. It has 11 electrons. You agree? It's like 1 neon plus 1 electron. So those 10 electrons are very tightly bound to the atom, the nucleus. So they form the ion, core electron. And the 1 electron in sodium love to give away whenever it remains out. So that is the valence. Okay. So similarly, you have a set of valence electrons and a set of core electrons. Core electrons and nucleus, they form one entity. So in your Hamiltonian, you don't want to treat ion and nucleus, so core electrons and nucleus separately. You say that they together as ion. And often the valence electron is simply told as electron, because that is the one which loves to pop around, move around. Correct? So valence electron roughly sometime by habit, if you say. You can see here that this desire is fulfilled, all the states are filled. In fact, this is also filled. This is empty, so these are ready to form bond and hop around. These are like this forms of valence electron. This one neither this side nor that side of this Watson Nancy term. Neither at home nor at the bond side, right? So these are sometimes called semi-core, but you don't know. So leave them as like that. They correlate. Semi. Neither core nor valence, but most likely core. They don't participate. Okay. All I am talking electron structure of atoms and molecules. Okay. Once we know atoms and molecules, you have new eigenstates found. Molecules. Once you move from atom and molecule, you cannot define this discrete states, right? So you have new states formed. Let's ignore about the core electron states. For example, oxygen tube, you know that will be 1s for oxygen 1, 2s for oxygen 1, 1s for oxygen 2, 2s for oxygen. But what about the 2p states? So the 2p states of oxygen 1, let's say this is oxygen 1, this is oxygen 2, right? Ignore 1s, 2s. They are closely bound to the nucleus, so they don't contribute anything. They don't change. They are energy. So this state, let's say 2p states, three possible states with spin degeneracy, right? So you can define as LLQ. So this is from oxygen 1, this is from oxygen 2. Correct? Now, for both of them, these are like identical orbitals, energy structures. So when they form bonds, they develop a new set of states. They don't have any original states. Develop a new states here below. Some of them energetically lower and some of them energetically higher. Right? And by habit you call bonding, anti-bonding. So the bonding states will be start occupying first, then the anti-bonding state. Right? So the molecule electronic structure is very different from the atom electron. It depends on what kind of interactions they have. Either three-way schematic of it, this is not accurate, right? Now, what kind of chemical bonding you have heard about? Okay, let's list out. So, what do you mean by ionic? No, transfer, right? Sodium chloride, one electron is transformed from sodium to chlorine. Okay, in that case, they don't form bonding like this. So, electrons are permanently transferred. Chlorine needs one electron, sodium wants to release one electron. If chlorine gets that electron, its cells are fully filled. If sodium gives away that electron, its cells are fully filled. Now there are two fully filled atoms bond each other by transferring the electron. One becomes positively charged, other becomes negatively charged. Then you have an attractive Coulomb potential. Keep them together. That is a sodium chloride ion. Covalent bond where electrons are shared, right? Transferred. We will come to hydrogen. When electrons are shared, these states neither belong to oxygen 1 nor belong to oxygen 2. These states are joint product of oxygen 1. Similarly, these states are joint product of oxygen 1. So electrons of these states have some electron from 1, some electron from 2. Okay, that's how they share. They share the states of pairs. Correct? Now then hydrogen bonding. Hydrogen bonding story is a little different. Then you form a temporary dipoles and two dipoles try to have some interactions. Very different. I'll tell you what. People still have not understood bonding completely. People have not. So all our school teachers, like us, we say that so softly that okay, there's a covalent bond, there's a ionic bond, there's a hydrogen bond, that is this bond, that is that bond. Still we have not understood them completely. 2 days back, I saw one article in, I don't know how many of you have heard about this journal, Journal of American Chemical Society. It is one of the highly reputed international journal. So few people have tried to explain all these burnings in a very different way, moving away from the conventional way of explaining the bonding, because the conventional way of explaining the bonding has some issues, some doubts, some questions, some confusions. Therefore, they are trying to find a new definition. So, all we are trying to hand over. We are saying that electron move here, electron move there. We exactly don't know how they move there, how they move here, because it is lies in the quantum mechanical world. Okay. So, to redefine, they have tried to redefine these bondings in this new article in JAX. I forgot to bring the reference of this article, but I can share with you guys later. But whatever it is, we have now formed the bondings. You have new eigenstates. Now we have formed a molecule. Like you have many kind of molecules. The same kind of atom can be a diatomic molecule. You can have different atoms like NH2, H2O. All these molecules we have created. So, and the molecular states are created. So, let's now talk about the molecular states in a gaseous phase. So, we have, so these are kind of molecular states. It's a one single molecule, right? In a gaseous phase, all these single molecules, they stay far away from each other. Am I correct? Right? And all of you know this Coulomb interaction. So, what is the expression of the Coulomb force? You say Q1 Q2 by R square. So, the force goes by 1 by R square. So, as the R then this increases, the force decays rapidly. Okay. In the gaseous phase, the distance is so much so that this molecule doesn't have any force experience produced by this molecule. The electrons of this molecule do not see the force produced by electron of this molecule. So these eigenstates don't change. So individual molecular eigenstates or the individual molecular electronic structure is same as the electronic structure. Correct? Now what happens to if I bring them close a little bit to a liquid phase? Yes? Then I brought them close a little bit to a liquid phase. So what will happen? So this, if you bring them close to a liquid phase, these states will be perturbed little. They are not so close, they are not so far. In the case of liquid phase, they are not so close, so far. So there will be some influence of the electrons of this molecule on the electrons of that molecule. Some influence, but it's very minor. It's a perturbation. All of you have heard the word perturbation. Perturbation means minor disturbances. Minor disturbances, right? So these states may change a little bit. They may move some other states, something like that. Something. So these are no longer the old individual molecular eigenstate. They are perturbed a little bit, and still we can treat them as isolated. Okay? And their mechanics define rest of the properties like fluid mechanics. Not much change. However, when you bring them close to each other, When you bring very close to each other, like in tungsten or a iron metal bar, the molecules are so close to each other that they are rigidly attached. Am I correct? Okay. When they are rigidly attached, let's say you have one molecule here, another molecule here, another molecule here, another molecule. I'm just drawing a bunch of molecules. Something like that. Their distance is some. Then these electrons will interact with this electron, these electrons will interact with this electron, these electrons will interact with these electrons like that. They keep on interacting. The individual eigenstates won't stay as it is. Individual molecular eigenstates will not stay as it is. What will happen? Like in the case of I drew this diagram, no? They form bonding, anti-bonding. There is a series of bonding and anti-bonding interactions. A lot of interactions will happen. Now, these states will be much more denser. Just how many molecules are there in a solid in one mole? So many, 10 to the power 23. And at least around one, that will be 5, 6, 10 number of molecules will be there. Right? Now, imagine one oxygen atom has 8 electrons, 2 oxygen has 16 electrons. Let's say 8 oxygen or 8 such atoms are around. 16 into 8, how much is 148 or something? That many electrons are trying to interact with each other. So when they try to interact with each other, these individual states are no longer that discrete. You see, they are still discrete. These individual states will no longer be that discrete. They are so dense. So we started from very farly separated states, discrete states, right? They are far away from each other energetically, to little more close in a molecule. When it comes to solid, they are very dense. They are dense, so these are like forbidden zone. So Professor Mangalasundar have said that allowed energy eigenvalues, forbidden energy eigenvalues. So in the forbidden zone, there is no energy eigenstates can lie. There will be no energy eigenstates. Empty. These are bunch of states occupied. Bunch of states occupied. Bunch of allowed vectors, allowed eigenvalues. As if there is a band. What is a band? Forget electrons. Band baja bara. Have you heard this song? No? Band party? No? Any other explanation of band? What do you know in your local language? Band means a continuous spectrum in the universe. It has a minimum value, maximum value. Okay. So this is a continuous spectrum. It's no longer discrete. Continuous spectrum. Right? So the energies are so close that they are continuous. There is no discreteness allowed. So electrons. So suppose that these two states are very close, like nearly degenerate. Almost. One electron can happily move from one state to other. In this case, electrons cannot move until unless they occupy this much of energy. So in a band, the electrons can keep moving, right? So these bands are formed. So in solid, the electronic structure is defined by bands. Gives rise to band structure. We are not calling any more electron structure. We can happily call it a band structure because you have energy bands. Now, depending on the number of electrons available, either these bands are fully filled or partially filled or empty. Like you said, this state is fully filled, this state is fully filled, partially filled. These bands are fully filled or partially filled or empty. You don't know, depending on the number of electrons available. Okay. Now comes the next topic. Suppose your number of electrons are available such that this band is fully filled. All the states in this band are occupied. This is empty. No electron here. Correct? And there is a gap because this is forbidden. Immediately, some compounds will come to your mind when I draw this diagram. Huh? Very good. We'll talk about semiconductor. It is fully filled, empty, correct? There is a gap in between. If you apply some energy or you supply more electron, this state will be now little bit open. Okay. If this gap is small, we call semiconductor. What is the gap in silicon? 1.1. Germanium 0.7. Something like that. I may be incorrect. I'm just trying to guess. So, and if the gap is very large, you cannot trigger the electron to jump from here to here. If the gap is very large, like 3 electron volt, 4 electron volt, 5 electron volt, 6 electron volt, electron cannot jump from here and you call them an insulator. There is no electron to move around. Correct? Now imagine a situation where this is, okay, by the way, the nomenclature is such that this is called valence band. This is called conduction band. Why did I say valence and conduction band? You see, valence band should be occupied. The band which is occupied by the valence electron is called valence band. Now, why it is called conduction band? I told you guys that they are so close to each other that the electron can occupy energy and keep moving. So the kinetic energy can be there and electron start moving. That is possible when the states are empty. Suppose this is one electron or few electrons jump here. Right? They have a large energy range to move around. They can occupy the kinetic energy and they still die in that domain. Right? Because the total energy for a system, for a particle will be its kinetic energy and the potential energy. So they can occupy that kinetic energy. When they occupy the kinetic energy, what you say? The electron can move, its motion is allowed. Therefore, they can conduct. That's why this band is called conduction band. If some electrons you can inject into this band, there are a lot of space available for them to move around. That is called conduction. Correct? Now it so happens that if you take like iron, aluminum, copper, all these things, their picture is that this band is partially, partly filled. Correct? If this band is partly filled, already space is available to occupy additional energy in the form of kinetic energy and make the electrons move. And that is called metal. See, when we try to understand the properties of the electron transport in a solid, we just can employ the quantum mechanics, define the bands, try to see the occupancy. From the occupancy, you can tell that which compound can be a metal, which compound can be a semiconductor, which compound can be an insulator. All these things you try to define from electronic structure in solid state. This was a big draw in 30, 40, 50 years back when the world started designing the electronic chips, the semiconducting chips. Why they call Silicon Valley in California? Because they developed the electronic equipment using semiconductors. Okay? And at that time, people started looking out materials which have a narrow gap so that they can have electron transport as their own, based on their own width. And the chips are from your gadgets, your mobile phone, all electronic equipments are based on this narrow bandgap system and mostly by silicon. Mostly by silicon. All your computer chips are still now even primarily by silicon. And your electricity is primarily by metals. Aluminum, copper, iron, and all these things. Okay? And all these things are explained using the solid state physics. Or the band structure or electron structure in solid state. Okay, now you can ask that now the world has understood semiconductor. There is nothing more left for the world to understand. Now, why do we need to study the solid state physics again and again? What is new? What we should expect from solid state physics in future? Any of you have any idea? Semiconductor, everybody has understood. We have found the best metal in the world. Aluminum, copper, all we know how much, what is their conductivity, what is their resistivity, and all these things we have found. What next in electronic structures? Let me ask that question. With that, we will end the discussion. Maybe a little more on what is in future for solid states. I'm not talking about mechanics. What Shivakumar taught is mechanics. I'm talking about electronics, electronic structure or band structure or this and that. So what is there in future? All of you have heard only electronics. I'll write few terms and let me see how many of you have heard about it. How many of you have heard about spintronics? Say yes or no, loud. Okay. How many of you have heard about orbitronics? Yes or no? How many of you have heard about topotronics? How many of you have heard about Vanitronics? How many of you have heard about Picotronics? See, you only know about it. So many projects are there. And all of them are very ill-defined and less understood. All of them are very ill-defined and less understood. And all of them build the future of us.